The story of Max Planck's revolutionary idea that energy is quantized begins in an era when physics was certain of itself, confident in its classical foundations, and convinced that the natural world followed smooth, continuous laws. During the late 19th century, physicists believed they had reached the pinnacle of understanding. Newton had mapped the motion of planets, Maxwell unified electricity and magnetism, and thermodynamics appeared to explain the behavior of heat and energy. Within this seemingly complete structure, scientists felt that everything left to discover involved simply polishing details. No one expected the foundations of physics to tremble, yet beneath this confident surface, one problem quietly resisted every attempt at explanation. That problem was Blackbody radiation, the mysterious way objects emitted light when heated. It seemed trivial at first glance. After all, people had been heating metals, watching furnaces glow, and observing hot coals for centuries. But mathematically describing how the glow changed with temperature seemed impossible. Every classical theory broke down, and predictions failed miserably. Something was wrong, but no one could identify what. Max Planck, a German physicist known for his disciplined nature and deep respect for established scientific laws, entered this arena not as a rebel seeking to overthrow old ideas, but as a careful, conservative thinker. Planck had no intention of initiating a scientific revolution. He simply wanted to understand the relationship between temperature and radiation. He believed that by applying classical reasoning cleverly, he would solve the puzzle peacefully within the existing framework. The universe, he assumed, must follow continuous rules. Energy must flow in smooth waves. Light must behave exactly as Maxwell described. There could be no exceptions. Yet as Planck studied the behavior of heated objects, he encountered a wall of contradictions. Experimental data demonstrated a pattern classical physics could not reproduce. The equations that predicted radiation at low frequencies failed at high frequencies. Attempts to adjust the formulas led to absurd predictions, including the infamous ultraviolet catastrophe, which claimed hot objects should emit infinite energy at high frequencies, something obviously false. Nature was whispering a truth no one wanted to hear. Classical physics was incomplete. Planck, however, persisted. He believed that the right mathematical trick could force the theory to match reality. After countless attempts, he produced a formula that miraculously fit every experimental curve. At first, this seemed like a triumph, but a deeper question immediately surfaced. Why did it work? What physical principle lay behind it? Planck realized his formula only made sense if energy didn't behave as a continuous flow. Instead, energy behaved as if it came in discrete packets, tiny, indivisible units proportional to the frequency of radiation. This was a shocking thought. Nothing in classical physics allowed such a possibility. To say that energy came in chunks of violated centuries of scientific understanding. But Planck had no choice. He introduced a new constant, a tiny number that defined the size of these energy packets. This constant, now known as Planck's constant, symbolized a boundary between the classical world and a deeper, hidden structure of reality. Planck initially treated this idea as a mathematical convenience, not as a literal description of nature. Even he hesitated to accept the radical implication that energy itself was not continuous. But the consequences of his idea grew rapidly. By proposing that energy is quantized, Planck had opened a door that could never be closed again. The classical world suddenly appeared as a surface layer, beneath which quantum behavior ruled. Each packet of energy was indivisible, and transitions between energy states occurred in jumps rather than gradual changes. This was a complete departure from Newtonian logic. Yet no matter how strange the idea seemed, it explained everything classical physics could not. It matched data perfectly, it resolved the ultraviolet catastrophe, and it introduced a new landscape filled with mysteries waiting to be explored. In the years that followed, Planck's insight began to penetrate the scientific community. Most physicists initially resisted the idea because it contradicted their deepest assumptions. They were trained to believe that nature was smooth, predictable, and continuous. The concept of discrete energy packets felt incompatible with common sense. But nature does not bend to human expectations. Experiment after experiment confirmed Planck's strange idea. The universe, at the smallest scales, behaved like a series of steps rather than a sliding ramp. Energy came in precise chunks, never in fractions of those chunks. Planck's constant became the defining scale of this hidden quantum world. It was unimaginably small, yet it governed everything from atoms to stars. One of the first major confirmations of Planck's idea came through Albert Einstein, who used energy quantization to explain the photoelectric effect. When light strikes a metal surface, electrons are sometimes ejected. Classical physics predicted that increasing the intensity of light should increase the energy of ejected electrons. But experiments showed otherwise. Only light above a certain frequency could remove electrons, no matter how intense the beam. This made no sense in classical terms. Einstein realized the solution lay in Planck's quantization. Light itself must consist of packets of energy, later called photons. These packets carried energy proportional to their frequency. If the frequency was too low, no amount of light could eject an electron. This confirmed Planck's idea in a completely independent context. The scientific world could no longer ignore it. As time passed, quantization became the foundation for atomic physics. Niels Bohr used it to describe the structure of atoms, showing that electrons could only occupy certain allowed energy levels. They could not move continuously between levels, they had to jump. These quantum jumps became one of the most famous and baffling aspects of the new quantum theory. Planck's idea had grown from a small mathematical tool into a universal principle. It governed atoms, molecules, radiation, and eventually all of quantum mechanics. Without quantization, there would be no explanation for chemical bonds, spectral lines, or even the stability of matter. Everything depended on the discrete nature of energy. Yet what makes Planck's discovery even more remarkable is his own reaction to it. He did not immediately embrace the philosophical implications of quantization. For years, he attempted to reconcile his constant with classical ideas. He believed that nature must still be continuous at some deeper level, and the quantization he discovered was perhaps a useful approximation. But the universe had spoken otherwise. Experiments increasingly showed that quantum behavior was real, fundamental, and inescapable. By the time quantum mechanics matured in the 1920s, Planck's constant had become the heart of the new physics. It appeared in every major equation, from Heisenberg's uncertainty principle to Schrödinger's wave mechanics. The entire structure of modern science rested on the idea that energy is quantized. To fully appreciate the revolution Planck ignited, one must imagine the world before his discovery. Classical physics portrayed the universe as a smooth machine. Every event followed logically from previous events. There was no randomness, no discontinuity, no sudden jumps. Everything moved according to deterministic laws. But quantization shattered that picture. It revealed that at the smallest scales, the universe behaves in ways that defy classical intuition. Energy does not flow like water, it behaves like counting beads. Light does not wave endlessly, it comes in packets. Atoms do not move smoothly, they leap. This new world showed a universe far more complex, mysterious, and dynamic than anyone had imagined. Planck's idea also influenced the development of technology. The entire digital age can trace its origins back to quantization. Semiconductors, transistors, lasers, LEDs, MRI machines, atomic clocks, and even quantum computers depend on quantum principles born from Planck's insight. Without quantization, electronics as we know them would not exist. The modern world runs on quantum physics, and quantum physics begins with Planck's discovery. His constant is not just a scientific parameter. It is the foundation of everything that makes the 21st century possible. Despite the profound impact of his discovery, Planck remained humble. He often reflected on how he had arrived at the idea almost reluctantly, stepping into unknown territory because the data forced him. He once said that he did not seek to overturn classical physics, but simply wished to solve a stubborn problem. Yet by daring to follow evidence wherever it led, he uncovered one of the deepest truths about the fundamental structure of nature. His constant became a portal into a realm where classical intuition collapses and new laws take over. The quantization of energy became the gateway to the quantum era. Planck's moment of realization is often depicted as the spark that changed everything. It was the point where physics shifted from certainty to possibility, from classical clarity to quantum mystery. His idea demonstrated that even in a world dominated by established theories, a single new concept could transform all understanding. Quantization revealed that the universe is not governed by smoothness, but by discreteness, not by intuition, but by mathematics, not by continuity, but by the strange, unpredictable behavior of quantum systems. In this sense, Planck's discovery represents more than a breakthrough in physics. It symbolizes the power of human curiosity, the courage to challenge assumptions, and the willingness to accept uncomfortable truths. It reminds us that progress often begins where certainty ends, and that revolutions can arise from the quiet persistence of a thinker seeking simple clarity. What started as an attempt to solve a modest problem became the foundation of a new world. Even today, physicists continue to explore the implications of quantization. The quantum world remains full of puzzles, entanglement, superposition, tunneling, and the nature of measurement. Yet the core principle underlying all these phenomena is Planck's original insight. Energy is quantized. The universe is built not from smooth waves, but from discrete units of action, each defined by Planck's constant. The entire structure of modern physics stands on this small but powerful number. Planck's discovery teaches us that the universe often reveals its deepest secrets in unexpected places. A small contradiction in a data set, an unexplained curve on a graph, or a persistent anomaly can signal the edge of a great unknown. Planck listened to those whispers, and in doing so, unlocked a door to a new reality. His constant remains a symbol of the quantum world, a reminder that beneath the familiar lies the astonishing. Through his insight, Planck changed not only physics, but the very way humanity understands the universe. As the scientific world slowly absorbed the shock of Planck's proposal, it became increasingly clear that the idea of quantized energy was not an isolated anomaly, but a universal feature of nature. Yet the journey toward acceptance was not straightforward. For many physicists, the leap from continuity to discreteness felt almost unthinkable. The classical world, was elegant predictable, and deeply intuitive. It matched daily experiences and aligned with centuries of intellectual tradition. To accept that energy came in fixed packets, rather than infinitely divisible amounts, meant reimagining the foundation of reality itself. But the evidence continued to mount, and it became impossible to retreat into the comfort of old assumptions. Planck himself initially believed that the quantization of energy was only a temporary device, a mathematical trick necessary to correct a flaw in existing theory. He hoped that further analysis would reveal a classical explanation lying beneath the discrete mathematical structure. Yet every attempt to reinterpret his constant within classical logic failed. Experiments consistently pointed toward a deeper truth. Nature was not continuous in the way humans had believed. Even though Planck was the father of the idea, he struggled emotionally and intellectually with the radical shift it demanded. He once admitted that he introduced quantization against his will. But the universe does not concern itself with human preferences. Over time, even Planck had to acknowledge that quantization was not a convenient approximation, but a fundamental law. The early 20th century became a period of rapid transformation as scientists encountered more phenomena that required quantization for their explanation. For example, atomic spectroscopy had long revealed that atoms emitted light at very specific frequencies, forming beautiful, precise patterns known as spectral lines. Classical physics could not explain why only particular frequencies were allowed. It predicted that electrons should orbit the nucleus-like planets orbiting the Sun, gradually radiating energy until they spiraled inward, a prediction clearly contradicted by the stability of matter. Yet, when Bohr applied Planck's quantization to electron orbits, everything suddenly made sense. Electrons could only occupy specific energy levels, and they emitted or absorbed packets of energy when jumping between these levels. This insight transformed atomic theory and confirmed that quantization was not merely a feature of light, but an intrinsic property of matter itself. As more discoveries accumulated, quantization emerged as a universal language spoken by the cosmos. It shaped not only the behavior of electrons and photons, but also the structure of atoms, molecules, and solids. It became clear that without quantization, matter would collapse, chemistry would not exist, and the universe as we know it would be impossible. Everything depended on the rule that energy changed in steps rather than a smooth continuum. Planck's constant set the size of those steps, acting as a kind of ruler for the quantum world. This tiny number, unimaginably small by everyday standards, defined the boundary at which classical intuitions failed and quantum phenomena dominated. This realization led physicists to rethink even the most basic assumptions about reality. The deterministic universe of Newton and Maxwell began to give way to a more probabilistic and mysterious picture. Heisenberg's uncertainty principle showed that certain pairs of properties, such as position and momentum, could not be simultaneously known with perfect accuracy. Schrödinger introduced wave functions to describe the likelihood of finding particles in particular states. All these new ideas were built on the foundation of quantized energy. Planck's constant appeared in every major equation, a silent witness to the birth of quantum mechanics. Yet quantization had consequences beyond physics. It challenged philosophical ideas about predictability, causation, and the nature of knowledge. In the classical world, everything was governed by strict, unchanging laws, and if one knew enough information about a system, one could predict its future perfectly. Quantum mechanics shattered this confidence. It revealed that at the smallest scales, probability ruled. Events did not simply happen because they were determined. They occurred because certain outcomes were more likely than others. Energy quantization was the first crack in the classical belief that the universe was a giant, predictable machine. This new perspective inspired both excitement and discomfort. Some scientists embraced the mystery, recognizing that the universe was far richer and more complex than previously imagined. Others resisted the philosophical implications. Einstein famously disliked the probabilistic nature of quantum theory, remarking that God does not play dice with the universe. Yet even he could not deny the accuracy of the theory's predictions. He had used quantization himself to explain the photoelectric effect, and despite his reservations, he contributed to the early foundations of quantum mechanics. The debate over the meaning of quantization revealed the profound impact Planck's idea had on the scientific community. It was not merely a mathematical adjustment, it was a revolution in thought. As the quantum era unfolded, the practical implications of quantization began to appear in technological advances. Lasers, for instance, rely on atoms absorbing and emitting energy in discrete amounts. Without quantized energy levels, there would be no stimulated emission, and laser light could not exist. Similarly, the behavior of electrons in semiconductors depends on quantized energy bands. Modern electronics, including computers, smartphones, and digital sensors, all rely on these quantum principles. Planck's discovery, originally born from a theoretical puzzle, eventually reshaped everyday life. Humanity unknowingly interacts with quantum physics every time it uses a GPS device, makes a phone call, or views an LED display. Even medicine benefited from Planck's insight. MRI machines use quantum principles to manipulate atomic nuclei inside the human body, creating detailed images that revolutionized diagnostics. Atomic clocks, which keep time with astonishing precision, rely on quantized energy transitions. They form the basis of global timekeeping and GPS navigation. Without Planck's constant, these technologies would not exist. Quantization is not simply a scientific curiosity. It is the foundation on which modern civilization stands. In addition to technological transformations, quantization deepened our understanding of the universe. In astrophysics, quantum mechanics explains why stars shine, how they evolve, and what happens when they collapse. The energy emitted by atoms inside stars follows quantum rules, allowing us to study the cosmos from millions of light years away. Even the behavior of exotic objects like neutron stars and black holes involves quantum principles. At the large-scale structure of the universe, cosmology intersects with quantum physics to explain the earliest moments after the Big Bang. Planck's constant plays a role in determining the fluctuations that eventually gave rise to galaxies. Thus, the idea that energy is quantized extends from the smallest particles to the grandest structures of the cosmos. Yet perhaps the most profound aspect of quantization is the way it shifted humanity's relationship with the unknown. Before Planck, physics seemed like a nearly complete discipline, with only minor details left to explore. After Planck, physics became an open frontier again, full of mysteries waiting to be uncovered. His discovery reminded scientists that nature often hides its deepest secrets behind everyday phenomena. The simple problem of Blackbody radiation, involving the glow of hot objects, turned out to hold the key to an entirely new understanding of reality. This lesson remains relevant today. Even the most ordinary observations can carry profound implications. Planck's willingness to question assumptions, follow evidence, and accept uncomfortable conclusions exemplifies the scientific spirit. As the decades passed, Planck's quantization became so deeply embedded in physics that it was no longer debated but taken as a fundamental truth. The constant that bears his name, symbolized by the letter H, is now used to define the very units of measurement upon which science relies. In 2019, the kilogram was redefined based on Planck's constant, meaning our global system of measurement is anchored to his discovery. This change reflects how central quantization has become to human knowledge. It is not only a scientific principle, but a universal standard, as essential as any law of nature. Planck lived to see the early stages of the quantum revolution, though he could not have predicted just how far-reaching his idea would become. He witnessed Bohr's model of the atom, Einstein's photon theory, and the unfolding debates about the interpretation of quantum mechanics. Yet he did not live long enough to see the full impact of quantum physics on technology, cosmology, and modern culture. But the legacy of his idea endured, expanding far beyond what he could have imagined. Planck's constant became a symbol of the boundary between classical intuition and quantum reality. It marked the threshold at which the familiar world gives way to a realm governed by rules that defy common sense. The story of quantization is, in many ways, the story of human humility. It shows that even the most confident theories can be overturned by the smallest contradiction. A simple mismatch between theory and experiment led to the discovery of a hidden structure beneath the observable world. Planck's constant, a number so small that it seems insignificant, became the foundation of an entirely new scientific framework. It reshaped not only physics, but humanity's understanding of existence. It revealed that certainty is an illusion, and that progress often arises from questions no one expected to ask. Planck's idea remains one of the greatest intellectual achievements in history. It demonstrated that the universe is more mysterious, more mathematical, and more astonishing than classical physics ever imagined. It showed that reality is built from discrete units of action, each governed by a constant that connects energy and frequency. This small, subtle idea changed everything. From the moment Planck introduced quantization, the universe could never again be seen through classical eyes. The quantum world had been revealed, and its implications continue to unfold even today. With his discovery, Max Planck not only solved a scientific puzzle, but altered the trajectory of human thought. He opened a doorway to new theories, new technologies, and new ways of understanding the cosmos. In doing so, he earned a place among the greatest thinkers of all time. His introduction of quantized energy remains one of the most transformative ideas in the history of science, a constant that truly changed the universe. The story of how Max Planck's constant became the foundation of quantum physics begins long before the constant itself had a name, a symbol, or even a place in scientific thought. It begins in an era where classical physics stood confidently atop centuries of achievement, shaping a world that believed it had uncovered nearly all the fundamental laws of nature. Physicists at the end of the 19th century were convinced that the universe behaved like a grand, continuous machine, every movement predictable, every interaction smooth, and every phenomenon governed by established principles. It was within this intellectual environment, seemingly complete and comfortable, that a single constant emerged quietly, almost reluctantly, and reshaped the destiny of science. Max Planck did not set out to create a new branch of physics or to overturn classical beliefs. His journey toward discovering what would later be called Planck's constant began with his effort to understand Blackbody radiation, an unsolved problem that defied the predictions of classical theories. Heated objects emitted light in patterns no equation could correctly describe. Some formulas predicted infinite energy at high frequencies, a result so absurd that physicists called it the ultraviolet catastrophe. Yet despite the dramatic name, few scientists recognized the depth of the problem. They saw it as a technical issue rather than a fundamental flaw in their world view. Planck, however, sensed something deeper. He believed that beneath the confusion lay a truth, waiting to be uncovered, but he could not have imagined that this truth would force physics into an entirely new era. After years of work, trial, and frustration, Planck found himself confronting an equation that matched experimental data perfectly. But the equation came with a price. It demanded that energy be emitted in tiny, discrete units proportional to a new constant. This constant, a number unimaginably small, carried profound meaning. In mathematical terms, it linked energy to frequency. In physical terms, it marked a boundary between the familiar classical world and the strange, unseen quantum realm. Though Planck introduced the constant reluctantly, he recognized its necessity. Without it, his equation would collapse. With it, the experimental curves aligned with elegant precision. At first, the constant seemed nothing more than a mathematical parameter. Planck treated it cautiously, unsure whether the discrete nature of energy reflected a fundamental property of nature or merely a useful tool for solving an otherwise intractable problem. But as time passed, the constant began to show itself in unexpected places. It appeared in equations describing light, radiation, atomic behavior, and the interactions of particles. Each time it emerged, it brought order to phenomena that classical physics could not explain. Slowly, the scientific community realized that the constant was not optional, it was essential. The moment this tiny constant entered physics, it began to reshape the field from the ground up. It revealed that energy was not continuous but quantized, shattering one of the core assumptions of classical theory. It suggested that the universe contained a fundamental scale, a smallest measurable action, below which nature behaved in ways humans had never imagined. This revelation did not merely fix a flaw in existing equations. It demanded the creation of an entirely new framework. What began as a solution to a minor problem in thermal radiation became the cornerstone of quantum physics. Albert Einstein was among the first to recognize the significance of Planck's constant. He used it to explain the photoelectric effect, demonstrating that light behaved not only as a wave but also as a particle. Each particle, or photon, carried energy in amounts determined by Planck's constant. This insight earned Einstein the Nobel Prize and provided one of the strongest confirmations that the constant was not a mathematical trick, but a fundamental property of nature. It proved that light itself obeyed Planck's rule and that the constant governed interactions at the most basic level. As more discoveries followed, the importance of Planck's constant grew. Niels Bohr applied it to his model of atom, where electrons could only occupy specific orbits with energies spaced according to the constant. Without this quantization, atoms would collapse, matter would be unstable, and the structure of the universe would be impossible. Planck's constant explained why atoms had fixed sizes, why spectral lines appeared at specific frequencies, and why matter behaved as it did. It became the ruler with which the microscopic world was measured. By the 1920s, Planck's constant had become the signature of quantum theory. Werner Heisenberg placed it at the center of his uncertainty principle, which stated that certain pairs of properties like position and momentum could not be measured simultaneously with perfect accuracy. The constant determined the scale of this uncertainty. It showed that the quantum world was not simply a smaller version of the classical world, but a realm governed by entirely new laws. Erwin Schrödinger introduced wave mechanics, and even his famous equation relied on Planck's constant to define the behavior of particles as waves. Everywhere physicists turned, the constant appeared again and again, as if it were the keystone holding the arch of quantum theory in place. What made the constant so important was not its numerical value, though its small size symbolized the subtlety of quantum effects. Its significance lay in its role as the bridge between energy and frequency, matter and radiation, determinism and probability. It linked seemingly unrelated phenomena under a single principle. With one number, Planck connected the behavior of glowing metals to the structure of atoms, the emission of photons, and the underlying fabric of reality. The constant became the fingerprint of the quantum universe. As the 20th century progressed, Planck's constant became indispensable in fields far beyond theoretical physics. It influenced chemistry, explaining why molecules form and how they interact. It shaped materials science, determining the behavior of electrons in solids and the electrical properties of materials. It shaped electronics, providing the foundation for semiconductors and transistors. Without Planck's constant, there would be no modern computing, no lasers, no fiber optic communications, and no digital technology. The constant that emerged quietly from a heated hollow cavity became a cornerstone of civilization itself. Yet the importance of Planck's constant extends beyond technology. It revolutionized the philosophical understanding of the universe. Classical physics portrayed a world ruled by continuity, predictability, and determinism. Quantum physics, grounded in Planck's constant, revealed a world of discontinuity, unpredictability, and fundamental limits. It showed that the universe was not infinitely divisible, not perfectly knowable, and not governed by smooth, unbroken laws. At the microscopic scale, nature behaved in jumps and probabilities. Planck's constant represented the line between what could be known and what was fundamentally unknowable. It forced humanity to accept that some mysteries were not simply the result of ignorance, but built into the universe itself. As quantum mechanics matured, physicists began to appreciate the philosophical depth of the constant. It was not just a number, it was a statement about the nature of reality. It told scientists that the universe was quantized, that energy came in discrete pieces, and that at the smallest scales, nature behaved according to rules utterly different from human intuition. It revealed limits on measurement, on knowledge, and on the continuous models that had dominated science for centuries. The constant marked the border between the classical and quantum worlds, a threshold where everyday logic breaks down and quantum logic takes over. Even today, Planck's constant continues to shape scientific exploration. Quantum field theory, which describes particles as excitations of fields, relies on the constant to define interactions. Quantum electrodynamics, the most accurate theory ever developed, incorporates the constant in every calculation. Quantum computing, emerging at the frontier of modern technology, depends on quantum states governed by Planck's constant. From the smallest scales to the largest cosmic structures, the constant plays a role in shaping the universe. The redefining of the kilogram in 2019 stands as a testament to the constant's importance. Scientists replaced the old physical artifact, a metal cylinder, with a definition based on Planck's constant. This decision ensured that the unit of mass would remain stable and universal, tied not to a human-made object, but to a fundamental constant of nature. The fact that mass itself is now defined by Planck's discovery reveals how central the constant has become to human measurement and understanding. Looking back, the rise of Planck's constant from a reluctant mathematical parameter to the foundation of quantum physics is a story of intellectual transformation. It demonstrates how a single number can change the trajectory of science. It shows that even conservative thinkers, when guided by evidence, can uncover revolutionary truths. Planck himself had no intention of reshaping physics, yet he did so more profoundly than almost any scientist before him. His constant did not emerge from ambition, but from the humble pursuit of understanding. Its power lay in its necessity, nature demanded it, and Planck had the courage to listen. Planck's constant continues to symbolize the spirit of discovery. It reminds scientists that the universe is full of hidden structures waiting to be revealed, that old assumptions can crumble in the face of a small but persistent anomaly, and that the deepest truths often emerge quietly, without fanfare. It stands as one of the most important constants in the history of science, the foundation upon which quantum physics rests. Through it, Max Planck changed not only physics, but humanity's understanding of the universe. The significance of Planck's constant grew clearer as the scientific community gradually realized that this tiny number was not merely an incidental feature of thermal radiation, but a universal measure woven into the fabric of reality itself. Its arrival signaled the end of an era where classical physics reigned unquestioned and opened a new frontier where the rules of the microscopic world demanded a more profound, more mysterious framework. What began as an adjustment to match experimental curves unfolded into the cornerstone of a revolution. Physicists came to understand that Planck's constant was not just another constant like the speed of light or the gravitational constant. It was the scale that defined the limits of human comprehension within the quantum domain. As researchers applied this constant to various phenomena, they discovered patterns that classical theory had overlooked: the photoelectric effect, the stability of atoms, the discrete spectra of elements, and the behavior of particles in confined spaces all pointed to one truth. Nature was quantized, and the size of each quantum was determined by Planck's constant. It governed not only how energy was emitted and absorbed, but also how particles behaved, how waves interacted, and how matter was structured. The constant became a key that unlocked a hidden world beneath everyday experience, a world where intuition faltered and mathematics illuminated new truths. In laboratories across Europe, young physicists recognized that the constant created a boundary line dividing the predictable world of classical mechanics from the probabilistic world of quantum behavior. This line was not a physical boundary but a conceptual one. It represented the scale at which classical ideas collapsed and quantum rules took over. When a system was large compared to Planck's constant, classical physics worked beautifully, but when a system became small, comparable to the scale defined by the constant, quantum effects dominated. This revealed a universe that transitioned between two realms, depending on scale. Planck's constant served as the switch that determined which set of laws applied. One of the most striking implications came from Heisenberg's uncertainty principle. This principle emerged directly from the existence of Planck's constant. It stated that certain pairs of measurements could not be simultaneously determined with perfect accuracy. The constant represented the minimum graininess of action in the universe. It set a limit to the precision with which nature could be described. This was not a matter of imperfect instruments or human error. It was a fundamental characteristic of reality. The uncertainty principle shook the philosophical foundations of physics. It suggested that the universe was not built on deterministic pathways, but on probabilistic outcomes. Planck's constant lay at the heart of this new world, redefining what it meant to know and measure the world. As the quantum era deepened, Schrödinger's wave equation further highlighted the importance of the constant. His equation described the evolution of quantum states, but it required Planck's constant to relate wave behavior to actual physical quantities. Without the constant, the equation would be meaningless. The constant powered the entire mathematical machinery of quantum mechanics. It allowed wave functions to connect with observable properties of particles, bridging abstract mathematics to physical reality. Every solution to Schrödinger's equation, every probability distribution, and every predicted behavior depended on this constant. At its core, Dirac's work on relativistic quantum mechanics revealed yet another layer of significance. By combining quantum theory with special relativity, he discovered the existence of antimatter, a prediction confirmed by experiment. Planck's constant was present even in this advanced formulation, demonstrating that quantum behavior extended beyond slow, moving particles to the entire spectrum of physical processes. It became clear that the constant was universal, applying to everything from electrons to photons to the theoretical interactions governing the cosmos. It was not limited to one corner of physics, it permeated all of it. Planck's constant also shaped the emerging field of quantum field theory. In this framework, particles emerged from excitations of underlying fields, and the constant dictated the quantization of these fields. It determined the sizes of energy steps and influenced how particles interacted. Every creation and annihilation of particles followed rules governed by the constant. It became the language of the quantum vacuum, the scale at which virtual particles fluctuated into existence. Even the quiet emptiness of space was no longer truly empty but filled with activity determined by Planck's constant. The vacuum itself was alive with quantum motion, revealing a universe far more dynamic than classical physics ever imagined. While these developments reshaped the intellectual landscape of science, Planck's constant also began to affect daily life in surprising ways. Technologies we now take for granted, radios, microwaves, digital cameras, and medical scanners, depend on principles defined by this constant. The semiconductor revolution, which allowed computers to shrink from room-sized machines to pocket devices, relies on electron behavior inside materials, behavior that is entirely governed by quantized energy levels. Without Planck's constant, electrons would not follow these rules, and the transistor would never have been invented. Modern electronics, the Internet age, and digital communication all stem from quantum mechanics, and therefore from Planck's constant. Behind every scientific instrument that measures frequencies, energies, or atomic transitions lies the constant that Planck discovered. Even the most precise timekeeping devices on Earth, atomic clocks, operate by measuring energy transitions defined by this constant. Global satellite navigation systems rely on these clocks, meaning billion-dollar infrastructures depend on a number Planck introduced reluctantly more than a century ago. The constant has become a thread woven into the fabric of modern existence, connecting quantum laws to human technology. The influence of Planck's constant extends even farther into the cosmos itself. In astrophysics, quantum mechanics helps explain how stars produce light, how white dwarfs and neutron stars resist gravitational collapse, and how elements are forged in nuclear reactions. These processes rely on energy transitions and forces shaped by quantum principles. Even the behavior of black holes involves quantum mechanics. Hawking radiation, a prediction that black holes slowly evaporate, arises from quantum fluctuations at the event horizon, a phenomenon shaped by Planck's constant. Thus, the constant that began as a solution to a laboratory problem now plays a role in the birth, evolution, and fate of stars and galaxies. Cosmology, too, has felt the constant's influence. The early universe, mere fractions of a second after the Big Bang, was governed entirely by quantum fluctuations. These fluctuations, magnified over cosmic scales, seeded the formation of galaxies. The constant appears in models of cosmic inflation, quantum fields, and the earliest patterns imprinted in the cosmic microwave background. In a profound sense, the structure of the universe today is a large-scale consequence of quantum processes shaped by Planck's constant. Billions of years ago, despite its deep influence, Planck's constant retains an air of mystery. Why does the universe contain this particular value? Why is it so small, yet so essential? Physicists still debate the philosophical implications. Some see the constant as a fundamental number woven into the universe's design. Others argue it reflects deeper, unknown principles that humanity has yet to uncover. Whatever its ultimate meaning, its role is undeniable. It governs the scale at which quantum effects occur. If the constant were slightly different, the universe would look nothing like it does. Atoms might not form, chemical bonds might not exist, and life itself would be impossible. The delicate balance of creation depends on the constant that Planck revealed. Looking back at Planck's personal journey, the beauty of his discovery lies partly in its unexpected nature. He was not a revolutionary seeking to disrupt classical physics. He was a dedicated physicist who respected tradition and sought stability in scientific understanding. Yet the evidence forced him in a radical direction. He introduced the constant reluctantly, only because it was the sole path that aligned theory with observation. His honesty and discipline allowed him to follow the mathematics even when it contradicted his intuition. This intellectual courage is one of the defining aspects of scientific progress. The legacy of Planck's constant continues to expand. In the emerging field of quantum computing, the constant determines how qubits behave, how superposition functions, and how quantum coherence can be maintained. The potential of quantum computers to revolutionize cybersecurity, medicine, and artificial intelligence depends on principles rooted in Planck's discovery. Quantum sensors, capable of measuring gravitational waves or detecting tiny magnetic fields, also rely on the constant. These technologies mark the next frontier, where quantum principles transition from theoretical tools to practical instruments shaping the future. In the cultural imagination, quantum mechanics has become synonymous with mystery, with paradoxes, and with the idea that reality is more complex than it appears. Concepts like wave, particle duality, superposition, and entanglement have entered popular language. At the heart of all these ideas is Planck's constant, the quiet symbol of the boundary between classical certainty and quantum possibility. The constant reminds humanity that the universe cannot be fully grasped by intuition alone. It requires imagination, mathematics, and the courage to accept the unfamiliar. Planck's constant stands today as a testament to human curiosity and the relentless pursuit of truth. It represents the moment when physics stepped beyond the visible world and confronted the invisible structure beneath. It symbolizes the birth of a theory that not only reshaped science, but also redefined the limits of knowledge. It is a constant that whispers of the universe's deeper design, inviting scientists to explore realms still hidden and to question assumptions still held. From the glow of a heated object in a laboratory furnace to the behavior of particles in the vacuum of space, Planck's constant governs the universe at every scale. It bridges the worlds of the very small and the unimaginably large. It shapes the technology of today and the discoveries of tomorrow. It is the foundation of quantum physics, the cornerstone of modern science, and one of the greatest intellectual achievements in human history. This constant, once introduced with hesitation and doubt, became the key that unlocked the quantum universe. Through it, Max Planck transformed not only physics, but the human understanding of existence itself. The foundation he laid continues to support every advance in quantum theory, every leap in technology, and every new window into the cosmos. His constant remains a guiding star for scientists exploring the deepest layers of reality, a reminder that even the smallest numbers can carry the weight of the universe. The realization that Max Planck's work challenged the classical view of a continuous universe did not happen in a single moment, nor did it erupt like a scientific revolution announced overnight. Instead, it unfolded like a slow but unstoppable tide rising beneath the foundations of physics, quietly undermining ideas that had stood unchallenged for centuries. Classical physics had painted a picture of reality in which everything flowed smoothly, Predictably and continuously, space was continuous, time was continuous, energy was continuous, and motion followed deterministic laws that traced their lineage to Newton. The universe, as understood at the time, behaved like a perfectly crafted machine, and every part of it could, in principle, be described with infinite precision. Planck's discovery did not just modify this world, it pierced straight through its core. When Planck introduced the idea that energy came in discrete packets, he unknowingly lit a fuse that led to the collapse of the classical worldview. The notion that energy could not vary gradually, that it could only exist in whole, number multiples of a fundamental unit, was not merely a mathematical detail. It was a statement about nature itself. Classical physics assumed that any physical quantity could be divided endlessly, that between any two values lay another value. Everything from heat to motion was thought to vary smoothly, and there was no concept of abrupt jumps or limits. Planck's constant shattered this comfort. It said that energy had a smallest unit, and below that unit there was nothing smaller. It was as if nature itself was built out of invisible steps, not a smooth ramp but a staircase too fine for human senses to detect. This idea collided violently with the beliefs of the scientific community. Even Planck himself resisted its implications at first. He considered these energy quanta mathematical tricks meant only to salvage a failing theory of Blackbody radiation, but experiments piled up, and each one whispered the same truth. The universe was not continuous at its foundations. Light behaved like a stream of particles. Electrons occupied specific orbits rather than sliding smoothly through all possible positions, and atoms released energy in sudden jumps rather than gentle flows. The classical picture of the universe, once so solid, began to crack. Einstein pushed the brake further when he used Planck's constant to explain the photoelectric effect. His work showed that light did not transfer energy continuously, but delivered it in packets tied directly to Planck's constant. This was more than a correction to classical wave theory. It was an overthrow of continuity itself. If energy came in packets, if electrons jumped between levels instead of sliding, if radiation interacted through discrete quanta, then the smooth, fluid universe classical physics described was an illusion crafted by humans, scale senses. Beneath the illusion lay a world made of jumps, steps, and probabilities. One of the most striking consequences of challenging classical continuity was the emergence of uncertainty. Werner Heisenberg demonstrated that the precision of measurements had a natural limit set by Planck's constant. The more one tried to pin down a particle's position, the more uncertain its momentum became. Classical physics assumed perfect knowledge was possible with better tools. But quantum theory, built on Planck's constant, showed that the universe itself imposed boundaries on what could be known. Precision was not limited by technology, it was limited by nature. As quantum mechanics matured, the picture of a continuous universe faded into a relic of the past. Schrödinger's equations described particles as waves, but even these waves behaved according to quantization rules governed by Planck's constant. The orbits of electrons were not continuous loops, but probability clouds shaped by discrete energy levels. Even empty space, once thought to be a calm void, became a restless sea of quantum fluctuations, tiny bursts of energy appearing and disappearing, all governed by the same constant that Planck had uncovered decades earlier. The greatest irony was that Planck never intended to challenge classical continuity. He was a conservative thinker, devoted to the classical tradition, and deeply reluctant to accept what his calculations implied. Yet his constant forced him, and later the entire scientific world, to confront a new truth. The universe was not the smooth, predictable machine classical physics had imagined. Instead, it was a mosaic of discrete events, quantum leaps, and fundamental limits. Planck's breakthrough opened the door to a universe built not on continuity, but on quantization, revealing a deeper, stranger reality hidden beneath the surface of everyday experience. When Max Planck introduced the idea of energy quanta, he could not have predicted that this single step would pave the way for a new generation of thinkers who would transform physics more radically than any group before them. The constant he uncovered, and the quantization principle it carried, opened a door that others soon walked through: Einstein with bold leaps, Bohr with visionary interpretations, and many more who together built the structure of modern quantum mechanics. Planck did not merely solve a problem about glowing metal. He created a launching point for some of the greatest scientific revolutions of the 20th century. Einstein was the first to grasp the full power hidden in Planck's idea. While Planck saw his quantization condition as a mathematical fix, Einstein treated it as a physical truth. He dared to apply the quantum idea not just to energy exchanges in heated objects, but to light itself. With extraordinary courage, he proposed that light existed in discrete packets, later called photons, each carrying energy determined by Planck's constant. This was a fundamental shift, one that classical physics could not accept. Waves were supposed to be continuous, yet Einstein's photons acted like particles. This reconciliation of wave and particle through the quantum idea was the first major expansion of Planck's discovery, and it earned Einstein the Nobel Prize. Without Planck, Einstein would not have had the key needed to unlock this new understanding of light, and without Einstein's daring interpretation, Planck's constant might have remained an obscure parameter instead of a universal principle. Niels Bohr soon followed, taking the quantum idea deeper into the heart of matter, into the atom itself. At a time when classical physics could not explain why electrons didn't spiral into the nucleus or why atoms emitted light at specific colors, Bohr used Planck's constant as his guiding tool. He proposed that electrons could occupy only certain allowed orbits, each with energy levels determined by the quantum rule. When an electron jumped from one orbit to another, it emitted or absorbed a photon whose energy was tied to Planck's constant. Bohr's model was a daring blend of classical motion and quantum rules, and though not perfect, it worked beautifully to explain the hydrogen spectrum. It was the first true quantum model of matter. Planck had unknowingly provided the seed. Bohr nurtured it into a full-fledged theory of the atom. As more scientists worked with these ideas, it became clear that quantum theory was not just an isolated correction to classical physics. It was the start of a new scientific language. Planck's constant began to appear everywhere, like a signature of nature at the smallest scales. Werner Heisenberg and Erwin Schrödinger took the next great leap when they built full mathematical frameworks for quantum mechanics. Both of these frameworks, though different in appearance, relied fundamentally on the constant that Planck had first introduced. Heisenberg's matrix mechanics showed that the physical world at tiny scales behaved through non-commuting quantities, and the size of these effects was determined by Planck's constant. Schrödinger's wave mechanics revealed that matter could be described as a wave function whose behavior depended directly on the same constant. Each theory brought new clarity, and yet each pointed back to Planck's work as the starting point. The impact of this quantum revolution soon extended far beyond the early pioneers. Paul Dirac combined quantum mechanics with relativity, predicting antimatter and laying the foundation for quantum field theory. Louis de Broglie suggested that not only light, but all particles had wave-like properties, again scaled by Planck's constant. Everywhere the quantum idea spread, from the behavior of electrons in solids to the explanation of chemical bonds, the same constant reappeared. It became the universal stamp of the quantum world, telling scientists that beneath the calm surface of everyday life lay a reality governed by discrete actions and mathematical limits. What began as a reluctant adjustment in Planck's equations became the foundation of modern science. Planck opened the door, but it was Einstein who saw the path, Bohr who built the bridge, and others who expanded that bridge into a sprawling landscape of new knowledge. Quantum theory reshaped our understanding of atoms, molecules, light, energy, and information. It led to technologies such as lasers, transistors, and computers. It transformed philosophy by challenging determinism. It redefined what it meant to understand nature. Planck did not intend to spark a revolution, but once his constant entered physics, the world could never return to classical certainty. Through Einstein, Bohr, and the architects of quantum mechanics, his discovery became the gateway to a new universe, one more mysterious, more beautiful, and more profound than anything classical physics had imagined. When Max Planck introduced the idea that energy was quantized, he did far more than solve a mathematical puzzle. He changed the very lens through which scientists viewed the universe. Before his breakthrough, atoms were imagined as tiny mechanical systems governed by classical laws. Light was treated purely as a continuous wave, and reality itself was assumed to operate on smooth, predictable principles. Planck's work shattered that simplicity and replaced it with a deeper, more intricate picture, one where the fundamental pieces of nature behaved in ways no scientist had previously dared to imagine. His constant became the key that unlocked a universe built not on continuity, but on discrete rules, probabilities, and limits. The shift was so profound that it reshaped the scientific understanding of atoms, transformed the meaning of light, and ultimately redefined the structure of reality. It was inside the atom that the implications of Planck's discovery first revealed their power. Classical physics could not explain why atoms were stable, why electrons did not collapse into the nucleus, or why heated gases emitted light in sharply defined colors rather than a smooth rainbow. But once the idea of energy quanta entered the picture, everything changed. Electrons could only occupy certain allowed energy levels, and these levels were separated by amounts tied directly to Planck's constant. This meant that atoms were not miniature solar systems with electrons orbiting smoothly. Instead, they were governed by strict, quantized rules that allowed only specific arrangements. When an electron changed levels, it did not glide gradually but jumped instantly, releasing or absorbing a photon whose energy was fixed by Planck's constant. These jumps, unthinkable in classical terms, became known as quantum leaps, and they defined the behavior of matter at its most fundamental level. The stability of atoms, the colors of light they emitted, and the structure of the periodic table all trace their origin back to the quantization that Planck introduced. Light, too, underwent a dramatic transformation. Before Planck, scientists believed that light was purely a wave, a smooth oscillation spreading continuously through space. But the quantum idea revealed that light could behave as a particle, a photon carrying energy in packets determined by Planck's constant. This dual nature of light, part wave and part particle, was one of the most unsettling and revolutionary consequences of the quantum concept. It meant that light could not be fully understood through classical thinking. In some experiments, it spread and interfered like a wave. In others, it struck metal surfaces and ejected electrons like tiny bullets. This duality forced scientists to abandon the old idea that physical objects must behave in only one way. Light became the first and most striking example of a deeper truth. At the smallest scales, reality does not conform to everyday logic. Energy, motion, and even the identity of particles blur together in ways that defy classical expectations, and the scale of these effects is set by Planck's constant. As the implications spread beyond atoms and light, the structure of reality itself came under question. The assumption that nature operated continuously was no longer tenable. Instead, the universe revealed itself as a mosaic of discrete events, each governed by quantum rules. The smooth flow of energy was replaced by quantized steps. The precise predictability of motion was replaced by probabilistic outcomes. The solid certainty of classical objects dissolved into clouds of likelihood described by wave functions. These new features were not optional details. They formed the very fabric of reality at the microscopic level. Planck's constant served as the dividing line between the familiar macroscopic world and the strange quantum domain. Below this line, classical intuition breaks down, and the laws of nature become fundamentally statistical. This shift in perspective transformed the scientific understanding of existence itself. Reality became something dynamic, unpredictable, and deeply interconnected. Particles could behave like waves, waves could behave like particles, and the act of observation could influence the outcome of experiments. Objects no longer had definite properties independent of measurement. Instead, they existed in states of probability until observed. The universe was no longer a clockwork machine, but a realm of uncertainty, structure, and hidden order. At the heart of all these revelations lay the constant that Planck had reluctantly introduced, a number that determined the scale of all quantum effects. Planck's ideas did not simply update old theories. They forced the creation of an entirely new world, U. From the structure of atoms to the behavior of light, from the limits of knowledge to the nature of physical existence, the quantum revolution reshaped every layer of scientific thought. The universe, once imagined as predictable and continuous, became a place of discrete energies, fundamental limits, and mysterious depths. Through his constant, Planck gave science a new language for understanding reality, and that language continues to define modern physics to this day. When Max Planck introduced his constant at the turn of the 20th century, he could not have imagined that this tiny number, so small that it almost vanished into mathematical insignificance, would one day lie at the heart of the technologies that power modern civilization. At the time, his constant was a tool to explain Blackbody radiation, a theoretical puzzle that seemed far removed from practical use. Yet as quantum theory grew, Planck's constant became the universal signature of all microscopic processes. It appeared in the rules governing electrons, in the structure of atoms, in the behavior of light, and in the interactions between energy and matter. Slowly, quietly, and inevitably, it became the foundational ingredient in every device that relies on quantum mechanics. Without Planck's constant, modern technology would be unimaginable. It is woven into the mechanisms of lasers, the logic of semiconductors, the behavior of transistors, and the entire architecture of digital electronics. The story of its technological impact begins with the understanding that electrons inside solids do not move freely like tiny classical particles. Instead, their behavior is governed by quantum rules that define allowed energy levels and forbidden regions. These rules, shaped entirely by Planck's constant, determine how electrons jump between bands in a crystal lattice, how they conduct electricity, and how materials behave as conductors, insulators, or semiconductors. It is the quantized nature of these energy bands that made the semiconductor revolution possible. Every diode, every transistor, every microchip owes its existence to energy levels that depend directly on Planck's constant. When electrons move across a semiconductor junction, when they tunnel through barriers, when they release photons, their behavior reflects the quantum framework established by Planck's discovery. The transistor, the fundamental building block of modern electronics, operates entirely because electrons behave according to quantum energy levels. A transistor controls the flow of current by manipulating regions of allowed and forbidden electron energies. Without quantization, it would act like a simple switch with no precision, no control, and no amplification. But with Planck's constant setting the scale for electron behavior, transistors can regulate current with astonishing accuracy, enabling the creation of integrated circuits containing billions of components. Every digital device, from smartphones to supercomputers, depends on the quantum rules that flow from Planck's constant. It is no exaggeration to say that our digital world runs on a foundation laid by a constant discovered in 1900. Lasers offer another remarkable example. The operation of a laser relies on the idea of stimulated emission, a process in which an electron, already in an excited state, is triggered to fall to a lower energy level and emit a photon with identical energy, phase, and direction. This process only works because quantum mechanics dictates that electrons have specific, quantized energy levels, and that transitions between them produce photons with energies set by Planck's constant. Every photon produced in a laser has energy equal to the difference between these two levels, multiplied by Planck's constant. This precise, quantized control allows lasers to produce highly coherent beams of light, something impossible in a universe governed solely by classical physics. Lasers power fiber optic communication, medical devices, barcode scanners, industrial cutting tools, and even the atomic clocks that keep global navigation systems accurate. All of this is made possible by the simple rule Planck discovered: energy equals frequency multiplied by his constant. Quantum tunneling, another phenomenon tied directly to Planck's constant, plays a crucial role in technologies like scanning tunneling microscopes and modern flash memory. Tunneling allows particles to cross barriers they could not cross classically, because their wave, like nature, gives them a probability of appearing on the other side. This behavior is defined by equations that rely fundamentally on Planck's constant. Without tunneling, the electronic memory used in computers and phones would not function, because the ability to store and release charge in tiny structures depends on quantum probability, not classical flow. The influence of Planck's constant extends even to the realm of measurement. Atomic clocks measure time by tracking electrons jumping between quantized energy states, emitting photons whose frequencies are determined precisely by Planck's constant. These clocks keep global positioning systems accurate to within billionths of a second. A fraction of Planck's constant drifts and GPS fails, communication systems collapse, and power grids lose synchronization. In a very real sense, the stability of modern society rests on the stability of Planck's constant. What makes this story extraordinary is that the constant itself is unimaginably tiny, yet its impact is immeasurably vast. It governs the behavior of microscopic particles, and yet it shapes entire industries, technologies, and global systems. Planck sought only to understand a theoretical problem, but he ended up providing the key to the technological revolution. His constant bridged the gap between abstract physics and practical innovation. Every microchip, every laser, every digital signal, every modern communication network is a tribute to the quantum rules that Planck uncovered. His constant became the silent architect of our technological world, proving that even the smallest number can illuminate the largest possibilities. The influence of Max Planck extends far beyond the confines of his own era, echoing across decades of scientific discovery and shaping the very way humanity perceives the universe. His constant, introduced over a century ago, has become far more than a mathematical tool. It has grown into a symbol of the boundaries, the rules, and the hidden structure underlying reality. Planck's work laid the foundation for quantum mechanics, and from that foundation, entire new branches of physics have emerged. Yet its significance does not remain abstract or confined to laboratories. It reaches into cosmology, into the behavior of stars, into the origin of galaxies, and even into the philosophical understanding of what it means to observe, measure, and comprehend the universe. In this sense, Planck's legacy is not simply a historical achievement. It is an enduring framework through which the cosmos is continually explored. Planck's constant is the invisible thread that links the behavior of the smallest particles to the largest cosmic structures. In quantum mechanics, it defines the scale at which energy, motion, and action occur in discrete quanta. These tiny units govern how electrons orbit atoms, how photons interact with matter, and how chemical reactions proceed. At the microscopic level, this constant determines the stability of matter itself. Without it, electrons would collapse into nuclei, atoms could not form, and molecules essential for life would be impossible. Through this lens, Planck's legacy is not just theoretical. It is the backbone of existence. Life, chemistry, and matter obey the rules that emerge from his discovery, and understanding those rules has enabled humanity to manipulate the microscopic world in ways that were previously unimaginable. Beyond atoms and molecules, Planck's constant informs the study of light and radiation, which in turn drives advances in both technology and astronomy. The behavior of photons, their interactions, and their energy levels are all governed by this fundamental number. Observations of light from distant stars and galaxies, analyzed through quantum principles, allow scientists to deduce the composition, temperature, and movement of celestial bodies. Lasers, spectrometers, and advanced imaging technologies all exploit the principles stemming from Planck's constant, making the invisible visible, the distant measurable, and the previously unreachable accessible. Every observation of the cosmos at high precision depends, in subtle ways, on the rules he uncovered. In cosmology, Planck's legacy is equally profound. The very structure of the universe, from the formation of galaxies to the behavior of black holes, carries the imprint of quantum mechanics. Quantum fluctuations in the early universe, magnified during cosmic inflation, seeded the patterns that would eventually form stars, clusters, and galaxies. The constant defines the scale of these fluctuations and governs the probabilities of particle interactions that shaped the evolution of the cosmos. Even the radiation left over from the Big Bang, the cosmic microwave background, contains the fingerprints of quantum phenomena set by Planck's discovery. In this sense, his work is not merely a contribution to physics. It is an insight into the blueprint of the universe itself. Philosophically, Planck's discovery continues to challenge and expand the way scientists and thinkers conceptualize reality. The universe is no longer seen as a perfectly smooth, deterministic mechanism, as classical physics once suggested. It is a realm of probabilities, uncertainties, and discrete steps, where observation affects outcomes and the act of measurement carries fundamental significance. Planck's constant serves as a reminder that the rules of nature operate at scales beyond intuition, and that the universe may be stranger and more intricate than our senses alone can reveal. This perspective has influenced not only physics, but also fields like philosophy of science, information theory, and even the exploration of consciousness, where the boundaries between certainty and probability resonate with the quantum world. The applications of Planck's constant continue to grow as modern science pushes boundaries. Quantum computing, quantum cryptography, and advanced materials research all rely on principles derived from the constant. Scientists are exploring new ways to harness quantum states for information processing, to detect particles and energy at unprecedented precision, and to manipulate the fundamental structure of matter. The legacy of Planck's work is not frozen in history. It is alive, guiding contemporary research and opening possibilities that would have been unimaginable even a few decades ago. Every new quantum experiment, every measurement of subatomic phenomena, every investigation into the behavior of the early universe is built upon the foundation he laid. Max Planck's influence also extends to the human imagination. His discovery reminds us that the universe is not a simple place, and that even the smallest anomalies can lead to profound insights. A seemingly minor puzzle about Blackbody radiation, examined with rigor and curiosity, became the doorway to a revolution in understanding. Scientists today continue to confront puzzles that echo this spirit, knowing that the solutions to small questions can open vast new horizons. In this sense, Planck's legacy is both scientific and inspirational, a model of careful observation, intellectual courage, and willingness to follow evidence wherever it leads. In every quantum experiment, in every technology built upon quantum principles, and in every cosmological theory that links the tiniest particles to the vastness of space, Planck's constant is present. His work has not only transformed physics, but has also reshaped humanity's perception of the universe, revealing a reality that is intricate, discrete, and infinitely fascinating. The constant he introduced continues to guide exploration, enabling discoveries in physics, cosmology, and beyond. Planck's legacy is, therefore, timeless, a reminder that the pursuit of understanding, no matter how small the initial step, can illuminate the deepest truths of existence itself.